So the next presentation is by Kyle Davis, and the subject is enhancing the climate resilience of Indian agriculture through alternative grain production.
I've modified the title a little bit for brevity. Well, my name's Kyle Davis. Thanks, John, for the introduction. I'm an EI postdoc working with Ruth DeFries here at Columbia, and I'm also a NatureNet Science Fellow with the Nature Conservancy, working with Brian Richter and Joe Fargione, amongst my various other co-authors there. So today I'm going to talk to you a bit about the work that I've been doing in India, looking at the resilience and sensitivity of the production of different grains within the country to climate variability. So agriculture is one of the most important and direct ways by which humanity and the environment are linked. And in the coming decades, the global food system's going to not only need to increase the nutritious supply of food, but also enhance farmers' livelihoods, improve climate resilience, and minimize the environmental impacts of that additional food production. And amongst these various challenges, climate change is one of the more formidable for the global food system, and it's expected to have substantial impacts on crop yields. In the map that I'm showing you here, this is the percent expected change in yields from present day to 2050 under current agricultural management practices as a result of climate change. So you can see that there are expected to be impacts across all of the various regions across the world, and for the more industrialized regions like North America, Europe, and Australia, those impacts are expected to be less profound, whereas for places like Africa and Asia, the expected impact on crop yields is supposed to be more substantial. And of the developing regions, South Asia is expected to be one of the most impacted. So this presents some substantial challenges in terms of climate change adaptation, and South Asia and India both face substantial sustainability challenges more generally. And historically, India has, with mixed success, been able to meet the challenges of feeding a rapidly growing population. So on the positive side, the country has been able to feed an additional 900 million people since the 1960s, and it's been able to increase the average life expectancy of its population from 40 years to 68 years over that same time period. But on the flip side, there are still 191 million people within India that are chronically undernourished, and there are 180 million still living in severe water scarcity. So there's been mixed success in terms of achieving food security and sustainability goals within India so far, and these challenges are compounded by the fact that the Indian population is expected to increase by approximately 300 million people by the middle of the century. So with these sustainability challenges in mind, it's important that India and other large populous developing countries think about strategies that can better align food security and sustainability goals. And that comes comes examining which particular crops within their suite of available production options offer the greatest benefits in terms of achieving sustainability goals. So with that in mind, I asked the question, what is the sensitivity of Indian grains to variability in temperature and precipitation? And extending from that, I'm also interested in examining whether the crops that have the lowest sensitivity to temperature and precipitation variability also potentially offer other benefits in terms of nutrition and environmental outcomes. So climate projections for India agree in terms of how temperature is expected to change, where it's expected to increase, and depending on the socioeconomic pathway, the extent to which that increases, there's a large uncertainty associated with that. Precipitation patterns within India in the future, there's much less agreement amongst climate models, where some predict that there's expected to be an increase in precipitation overall, some predict a decrease, and it's highly uncertain where those increases or decreases might occur within the country. So by looking at historical data to assess climate resilience, that offers us one way to gain some insight into how specific crops produced within India may react to climate changes in the future. So to do that, I've combined a number of different data sets. I use district-level crop-specific production data, and this is reported annually. It reports yields, harvested area, and irrigated area. I've also used the high-resolution gridded soil grids data set, which reports information on soil texture. So that's the percents silt, sand, and clay. And then I've used a variety of different temperature and precipitation data sets and combinations thereof to ensure that the results of my analysis are robust against the specific outcome of a particular combination of temperature and precipitation data sets. So to estimate historical climate sensitivity within India, I've used a mixed effects modeling approach. And for my fixed effects, I use total monsoon rainfall and its squared term, mean daily monsoon temperature and its squared term. For soil texture, I use the percents sand and silt, and I don't include clay here because I ran into some collinearity issues. And then I also include the percent area irrigated by district and by crop. And then I also include random effects in this model to account for differences between districts and years. So I developed these models for each crop, and in doing so, I obtain coefficient estimates for rainfall variables and temperature variables. So that's beta 1 and beta 2 are the precipitation variables, and beta 3 and beta 4 are the temperature variables. And by comparing across crops the magnitude of a particular variable, I can begin to understand what the relative sensitivity of these crops are to historic variability in climate. So then, having developed these models for each of these individual crops, I can calculate what the yield would be under a typical climate year, and then I can also look at scenarios of extreme climate, either a minimum rainfall year or a maximum temperature year, calculate what the yield would be under that scenario, and then take the difference from the expected yield under a typical climate to assess what the change in yield would be under an extreme climate year. So as a first pass, I developed models at the national level for finger millet, maize, pearl millet, rice, and sorghum. And these are all crops that are cultivated during the monsoon season. So I'm not including wheat here because that's only cultivated during the winter. So what you'll notice is that for the precipitation variables P and P squared, I found that there was a significant relationship between precipitation and yield for pearl millet and rice. And then for temperature T and T squared, I found that there was a significant relationship for maize and rice. And for all of the crops except sorghum, I found that there was a significant positive relationship with irrigation, which is not at all surprising. And then marginal R squared is the fraction of the variance that's explained by only the fixed effects, excluding the random effects. And conditional R squared is the fraction of variance that's explained by the entire model. So looking at all of this, the models perform fairly well, at least as a first approximation. And at least initially, it seems that rice is generally a bit more sensitive to variability in temperature and precipitation as compared to some of these other crops. But because of the differences in geography and where these crops are actually cultivated, it's important to better control for that. So in order to do that, I developed state-level models for each crop and only considered those districts where a particular alternative crop, and by alternative crop I mean finger millet, maize, pearl millet, or sorghum, where a particular alternative crop is produced in the same district as that of rice. So here I'm showing the reduction in yield that would be expected under a minimum precipitation scenario, and the darker portion of each bar corresponds to the 95% confidence interval. So the orange bars correspond to each of the alternative grains, and the blue bars correspond to rice areas. So if we look at sorghum, the orange bar shows the reduction in yield expected under a minimum precipitation scenario, only considering those districts where both sorghum and rice are produced. And the same blue bar with sorghum is a model for rice, only considering those districts where rice and sorghum are produced. So I developed an individual model for each of the alternative cereals and 4 different rice models. And in doing that, I can look at whether the reduction in yield for an alternative cereal or for rice is larger or smaller and significantly different. So for sorghum, pearl millet, and finger millet, I found that under a minimum precipitation scenario, rice is expected to, the yields of rice are expected to be more greatly impacted than each of those alternative cereals, and that the opposite was true for maize, where maize yields are expected to generally be more impacted than rice. And I also ran the same type of analysis for a maximum temperature scenario. There wasn't that much interesting change, and if I run a scenario with minimum precipitation and maximum temperature, the results look very similar to what you see here. So this gives a general sense of the relative sensitivity of these different grains to climate variability, and overall rice and maize are more sensitive to rainfall variability. But it's also important to think about these a bit more in a bit more disaggregated way and in a more spatially explicit way. So I also developed maps comparing the sensitivity district by district of each of these crops compared to rice, and the blue areas in each map indicate places where the alternative cereal is less sensitive to precipitation variability as compared to rice. In the red areas, the opposite is true. And across all 4 of these different alternative cereals, there are some consistent patterns that emerge, especially in southwest India and in eastern India. You see that regardless of the alternative cereal that you might select, that cereal will be less sensitive to precipitation variability as compared to rice. But there are also lots of places where rice performs better as well. So from a policymaker's perspective, location is very important to consider when thinking about developing food security and sustainability solutions. So for some places, there's evidence that increasing the production of some of these alternative cereals can offer benefits in terms of climate resilience. And from a nutritional perspective, this also supports a transition in those places towards alternative cereal production and a bit away from rice. So if you look at the panel on the left, this is calorie content per 100 grams of each of these crops, and it's fairly comparable across all of those crops. And then if you look at the protein content, there's a bit more variability, but rice is still comparable to maize and finger millet and a lot of the other crops that could potentially replace it. But when you look at the iron content and the zinc content of rice, it's substantially lower than some of these alternative cereals. And then there's also the potential there's also an environmental argument that can be made in favor of a transition away from rice and towards some of these alternative cereals. So this is the amount, I'm showing you the amount of greenhouse gas emissions associated with the production of 1 kilogram of each of these crops. So it's the greenhouse gas footprint. And when we look at the emissions associated with fertilizer use, machinery, and irrigation pumping, they're fairly comparable across all of these different crops. But when we take into consideration the methane emissions associated with the production of each of these crops, rice really stands out. And we can also look at the water footprint, which is the volume of water required to produce a given amount of each of these crops. And there are fairly substantial differences in the total water footprint across all of these crops. But more importantly for India is the blue water footprint, which is the water that's provided through irrigation from surface and groundwater resources. And you can see that rice and wheat are the crops that rely most heavily on irrigation in order to meet their water footprint. And there are potential policy mechanisms that are already in place that can potentially realize transitions towards increased alternative cereal production in the places where policymakers might deem it feasible and appropriate. And one main mechanism is India's public distribution system, and this is a national program that provides minimum guaranteed price to farmers that are producing rice and wheat, and it also provides low-income households with subsidies to purchase that rice and wheat in the marketplace. And looking at the patterns of production, historical production and consumption within India, you can see that the public distribution system has played a large role. So in the panel on the left, I'm showing you the trends in cereal production through time, and you can see that rice and wheat have really come to dominate. And as a result, this has had important nutritional outcomes within Indian diets, where in the panel on the right, I'm showing you the per capita iron supply provided from cereals. And as these alternative cereals have received less attention within production, that's also meant that there's been substantially less iron supply per capita through time. So increasing alternative grains in certain regions can offer important benefits not only for climate resilience but also for nutrition and environmental outcomes. For future work, I plan to disaggregate the yields between rain-fed and irrigated croplands. I also plan to look at the input costs associated with the input costs that a farmer would have to incur in producing each of these different crops, and also examine where and to what extent diets would be flexible in incorporating these alternative cereals in lieu of rice. And in moving towards sustainable agriculture in India, it's important that policymakers not only consider nutrition, but also livelihoods, cultural preference, and the environment and climate change altogether. So thank you.
So we've got time for a couple of questions.
I was wondering whether in your... Hi, I'm Anand. I was wondering whether in your model, variety of rice variety, which I presume is quite different in different parts of the country, whether information is available and whether that would help in explaining some of the unexplained variables.
Yeah, that's a really good point, and information is fairly limited. To better get at that, I've tried to disaggregate between states, where I would assume that certain states might promote a particular variety, but that's something that's pretty difficult to capture given the available information. Yeah.
So it might be totally beyond your scope. And I have a question about, for example, the company Monsanto. How influential are they in the story? I mean, you look at data dated back to more than 60 years ago. I'm sure that during the past 60 years, they have adopted genetically modified seeds. And
Yeah, I don't know much about their specific role in India, but generally in terms of enhancing climate resilience of these different crops, there's been a lot more research dedicated to rice and wheat. So I would argue that that type of effort needs to be made for some of these alternative cereals as well.
Do you look into the effect of land use change over that 20-50 year period in India and how that then impacts either negatively or positively as far as production is concerned? Given that India is still a developing economy and it's growing at what, 8-10% at the moment?
By land use change, do you mean agricultural expansion, or do you mean differing management practices?
No, what I mean is basically you're eroding agricultural land for either residential, industrial, or manufacturing.
Okay. Again, I don't have a great idea of to what extent that's been an issue in India. I know that globally, about 2 to 3% of croplands have been displaced by urbanization. So I don't expect that would be a major factor, but again, I'm not entirely sure. Thanks.
I noticed in your data that some of the populations have a preference for rice as a nutritional diet element. And I was wondering, do you think that it would be possible to change their dietary patterns to achieve more nutritious outcome? Especially in regards to iron.
So the question was, there are lots of places where rice and wheat are culturally preferred, and do you think it'd be possible to transition towards increased alternative cereal consumption in those places? I think that's something, I think there's some flexibility there, but I think in those places there's probably less of a potential for transitioning diets. I mean, there's status associated with the consumption of rice in India. So, and a lot of the coarse grains in India either are consumed by poorer quantiles of the population or kind of the yuppie young upper middle class. So I think there are lots of places where alternative cereals dominate the cereal consumption basket. So those are places that policymakers might potentially want to focus on. All right. Oh, okay. Sure.
I just wonder, are mechanized systems generally more resilient? Are mechanized systems generally more resilient? So with urbanization, as like the mechanization and cooperativization, transitioning from subsistence to greater mechanization, does that stand to be a more resilient system?
Well, you'd expect with a mechanized system that they have access to a greater amount of resources that can cope with climate variability. So whether it's mechanization or access to fertilizers or the ability to implement irrigation, I think that offers the opportunity to buffer against some climate variability.
Thank you.
Thanks.